Great. So our next talk is going to be on the tight estimate of local leakage resilience of the additive secret sharing scheme and its consequence. Hi.
So thank you. This is our work with Maji, Anat, Tom, Mingyuan, Xiuyu, and Anat, and Mingyuan is here. So let me start with the notion of secret sharing. Go to the next slide. Sorry. So secret sharing is fundamental primitive. So it's a way to share secret as two parties so that any authorized set of shares can reconstruct the secret. And the security guarantee that any unauthorized set of shares reveal no information about the secret. And it has been shown that such an attack can be devastating, and it can break the security of crypto system. And put it into the context of secret sharing scheme, consider the case that the adversary can learn some password information from every share. For example, the adversary can learn 1 bit from every share. So now the question is that, is the secret still hidden? Okay. So liquid resilient sequencing ensure that the secret remains hidden. Okay. And Benhammer, De Cueva, Ishai, and Rabin formally define these notions and initiate study of local liquid resilient secret sharing. And Goya Kumar also implicitly and independently studies this primitive and in the context of non-malleable secret sharing. So since the introductions, there's been two main directions on this topic. The first direction is to construct a new secret sharing scheme that are liquid resilience. So as you can see, there are many fascinating works here. The main advantage of this approach is that it can achieve very high liquid resilience and against very wide class of leakage family. But however, this construction usually incur overheads, and it might lose the algebraic structure. For example, it might lose linearity or the multiplication family, and these properties are very important in applications. So another line of work is to construct liquid resilience of prominent secret sharing schemes. For example, the Additive and the Shamir. And this secret sharing scheme is used in many cryptographic protocols. So studying this in more precise risk assessment, and our work belongs to this line of research. So we study the liquid resilience of additive secret sharing scheme. So let me introduce the context of our work. So in additive secret sharing scheme, it samples shares S1 to Sk randomly, conditioned on the fact that their sums equal to S. And for this secret sharing scheme, any K-minus and shares are independent of the secret. So we also consider the local leakage model. So for this model, adversary can leak some password information about its secret, and this is non-adaptive and it was so independent. So a simpler model of leakage is a physical bit. So in this model, shares are stored in the binary representation. So the adversary can leak bits in the binary representations. So for example, the least significant bits is a physical bit leakage. So if the output value is 0, so it means that the shares is an even number. So here we are considering secret sharing over a brown field. And if the output value is 1, then it means that the shares is some odd number. So here are some very natural questions about the liquid resilience of a secret sharing scheme. So for example, what is the most devastating 1-bit local liquid attacks? And as a local liquid attacks more powerful than the physical bit liquid attacks, And we know that the local liquid attacks family are local liquid families is much bigger than the physical liquid family. So that just give us a lot of advantage on attacking the additive sequencing scheme. Okay. Or a similar question is like, what is the distinguishing advantage of the least significant bit leakage? So interestingly, if we look at the additive scheme of finite field of characteristic 2, then the least significant bit leakage it suffices to construct the whole secret. So this is shown by Gurusamy and Guterres, and their motivation is from repairing error coding codes, not from liquid resilience. Okay. And so this is somehow is very good in that setting, but in the perspective of liquid resilience, it is bad because here we can attack it, and the distinguishing advantage is one. It's not only non-eligible. So how does this question carry over the brown field? It is like the same, and the good news from liquid resilience perspective is that it's not that bad. So let me summarize the prior work and our contribution here. So in PDIR, they show that for any arbitrary local leakage, the distinguishing advantage can be at most the order of 2 pi to the k. So here we even allow computationally unbounded adversary. So we not require very efficient distinguisher. You can use any distinguisher, and the advantage can be at most the order of 2 pi. And if you can see, that is a green line, and the plot is log scale of the distinguishing advantage. Okay. So there's also that very local leakage attacks that have advantage of at least 1 by 2 to the k, and you can see it is the orange curve on the right. Okay. So as you can see, the gap here is quite large. Okay. So the upper bound and the lower bound is really far. So what is the best attacks? Is this in the middle? Is that close to the green line, or is that close to the orange line? Okay. So Anat show a physical bit attacks that is simpler, and the distinguisher is very simple. Okay. I will discuss this in more detail in the next slide. And they show that this physical bit liquid attacks had advantage of at least 1 by 2 to the k times k factorial. And that is the orange line here. And it's still very close to the lower bound in the BDR. Okay. So what is the truth here is that like the best attack is square that. Okay. So experimentally, Maji also that for small value of the number of parties k, it is the blue line. So we don't have any like theoretical bound here. So it's quite close to the green line. Okay. So our work proves that with the same physical liquid attacks, the distinguishing advantage is at least half of 2 pi to the k. So our contribution is to lift the curve from the orange curve to the red line, as you can see, and it is very close to the experimental result, and also close to the theoretical upper bound. Okay. But here I want to emphasize that this attack, the distinguisher is very efficient. We don't even need a lot of power on attacking this, and it asymptotically equivalent to the theoretical bound from the BDIR. So let me state our results more formal. First, I want to introduce the parity attacks. So this is a very simple attack. First, it links the missing bits of each share, and then it simply outputs the XOR of all the bits as a prediction of the secret. So our main theorem shows that for additive sequencing scheme over Bramfield among K parties, there are two secrets. So that the parity of parity attacks can distinguish the two secrets with advantage at least half of 2 by pi to the k. So consequently, if you want to ensure negligible distinguishing advantage, then the reconstruction threshold k need to be omega log lambda. So here, again, we want to emphasize that our text is optimal because the bound from the BDR show that it can be at most 2.47 2 by pi to the k. Okay. So the gap here is only the constant. Okay. So asymptotically, it's optimal. Okay. And here's some consequence of our results. First, I want to talk about the consequence to Xiuyu sequencing scheme. Okay. Let me briefly recall Xiuyu sequencing scheme. So to share secret S, it pick a random polynomial of degree S mod k minus 1, so that the evolution at 0 is equal to the secret S, and this shares as the evolution of the polynomial at distinct evolution places. For example, here the secret Si equal to evaluation of the polynomial at EI. So any K parties or K shares can reconstruct the secret using Lagrange interpolations. But any K minus 1 shares with no information about the secret. So our first corollary is say that for some sequencing scheme, there are adversary chosen evaluation places such that the parity of parity attacks on Xiuyu sequencing scheme has distinguishing advantage at least again that number 1 by pi times 2 by pi to the k. And similarly, to ensure negligible distinguishing advantage, one need k to be small omega log lambda. So this is for physical bit attacks. Now, if we consider the local liquid attacks, so the attacker can use any arbitrary local liquid functions. So for this one, we show that for any evaluation places, there is a 1-bit local liquid attacks, so that the distinguishing advantage is at least again the same number. Okay. And at a corollary, to ensure negligible locally liquid resilience, k need to be omega log lambda. So now let me interpret our result here to the state of the art. So here we want to plot the reason we know that for sure it's not liquid resilience. Okay. So the reconstruction test of k have to be less than n. So that's why the upper triangle is shaded. And the work of Nishan Kim show that if the reconstruction threshold k is less than n divided by lambda plus 1, where lambda is a security parameter, then the Xiuyu sequencing scheme is not liquid resilience. So as you can see, that is a green reason. So Anat also that if the reconstruction threshold is less than lambda by log lambda, then it is not liquid resilient. I want to emphasize that the attack in a Nishan scheme, it is non-explicit. So the probabilities arguments and they show that there exists some local liquid functions. But here's the middle attack is explicit, and again it is a parity attack. So I will work just lift the bound by Adam et al. To log lambda, and again it is same attack, parity attack. So this is the current state of the art, and for the why reasons it might be leakage resilience. So for all the stated reasons, we know for sure it's not leakage resilience. So here's are some other consequences, and I'm not going over the detail of this. And if you are interested in, you can take a look at our paper. So for the rest of the talk, I will be discussing this high-level technical overview. So our objective is to lower bound the distinguishing advantage of the parity attack. So it suffices to lower bound the statistical distance between the two leakage distributions. Okay. So here I will be more formal about the leakage distributions on a secret S. So it represents the Roy distributions over k-bit string that sample random secrets, a condition on the sum equal to the secret. And then it just outputs the leakage value. And we use, our approach is to use Fourier discrete Fourier analysis and an accurate estimate of an exponential sum. So previous work, they also use Fourier to prove the upper bound, but here we, so for the first time, you also use the Fourier to prove the lower bound. So the first step, similar to previous work, we can translate the statistical distance to the sum of the Fourier coefficients. Okay. So this is an application of the Poisson summation formula. And the statistical distance equal to sum over possible leakage value in the k-bit string, and then sum over the alpha in the non-zero alpha, and we have the product of two terms. The first term is a product of Fourier coefficients, and the other omega minus omega there is the difference of the two roots of unity. So I will explain that in more detail. And here's the notation 10 is an indicator of the even sets. So think about it is a Witness set for the leakage value being 0. And similarly for the set from 1 to p minus 2, that is a Witness set for the leakage value being 1. Okay. So our next step is to use the property of one-bit leakage functions, and basically we can simplify these expressions, and every term under the summand here has the same value. So that's why we can put to the power k here, and just looking at one term. So this term is an exponential sum, and our objective is to lower bound this exponential sum. Okay. So now the term under the summand is a product of two terms. So first we look at the first term. It is a product of Fourier coefficients. And here in the figure, we plot the Fourier spectrum of the 10. That is the Witness set of the leakage being 0. Okay. So as you can see, all the non-zero Fourier coefficient, it have exponentially decay pattern here. So only the two coefficients in the middle, they are large, and the rest of them, you can see it decay very fast. So it suggests that for the first term, when we raise it to the power k, it's decays very fast, exponentially. Now you will look at the second term, that is the difference of the two roots of unity. So the difference can be at most 2. You can see in the picture. So combining the two things, it suggests that the only two terms in the middle matter here. It's that those terms are the dominating term. The rest of them we can bound them. So basically we can say that we can use just only the two middle term to approximate the whole thing. So our job is just know about the two middle terms. So for these two middle terms, we have well understanding about that because as you can see from the previous picture, the Fourier coefficient is equal to 1 by pi. Okay. So if we have a term 1 by pi to the power k here, and now we just need to choose two different secrets S0, S1, so that when you substitute alpha equal to two middle values, this is not too small. The difference of the two roots is not too small. Then we are done. Okay. So here, I think it is quite easy to see this because actually the optimal value here, it can be like rapid too. So we can approximately by some approximate appropriate constant. So we get the derived bound. As you have seen a lot of time. Okay. So to conclude, the take-home message is that the elementary parity of parity attacks on the additive scheme is optimal. So that's all I have, and thanks for the attention.
Right.
Sorry, next talk is at 2:35.